Alright, everybody. Mic test, mic test. Okay, I guess you can hear me. Alright, everybody, and welcome to my channel. My name is Alex, and together we are going to work on programming problems. Just as we talked about last time, I'm trying something slightly different this time, which is I'm going to announce the problem we're going to work on next time so you can give it a try before we do it together. So last time around, I said we're going to do this problem, number 12, integer to Roman, which is a more difficult problem, a more difficult variation of the problem we attempted the last time, Roman to integer. This is a little bit trickier, and you're about to see why. But let's start as usual by reading the problem definition. Roman numerals are represented by 7 different symbols: I, V, X, L, C, D, M, and you have them here. 2 is blah blah blah. So this is fairly straightforward. This is not difficult, right? If this is the only thing that we have to care about, then all we have to do is take our number, write as many m's as possible until we're done with m's, and then write as many d's as possible until we're done with d's, and so on and so forth. Now, there is something tricky though. There is something tricky. Which is... okay, so as you see here, 12 is written as xii, which is simply x plus ii. So x is 10, I is 1, 2i, ii is 2, so xii is 12. Largest to smallest, left to right. However, the numeral for 4 is not III. Instead, the number 4 is written as IV. So the I is before 5, you subtract it, making 4. The same principle applies to the number 9, which is written as IX. There are 6 instances where subtraction can be used. So all the 4s and 9s. Okay. Alright, so here's what I'm thinking. Let me see, what's the largest number that we can get? Largest number is 4,000. Okay, 13999. Okay, awesome. Which means you'll never get at the most you will have to do MMM. There's no point of time where we have to do MMMM. Okay, so let's think about how we're gonna do this. It seems like one way I have of thinking about it. Initially, the way I thought about it was to count the number of M's, then count the number of D's, then C's, then L's, and so on and so forth. But now looking at this a little bit closer, I think the way I'm gonna do this is to break it down by digit. Essentially, in the thousands place, we have M and D. We in the thousands place, we use M and D. Yeah, sorry. In the thousands place, you just use M. I'm sorry. In the hundreds place, we use M and D and C. Okay, we use D and C. So depending on what digits we have in the hundreds place. So for instance, in the hundreds place, if we have 9 in the hundreds place, then we know it is CM because it's 1000 minus 10. Okay, so we have to use C, D, and M in conjunction for the hundreds place. And then for the tens place, we use sort of the same idea. We have C, L, and X. Okay, so basically the strategy is like this. Break it down by digit. For instance, in the hundreds place, 1. In the hundreds place, 1 would simply be C. 2 will be CC, believe that's right. Yeah, I'm pretty sure it's CC. And then the special cases, 4 will be CD, because that's 100 in front of the 500, we subtract it. And then 9 will be CM. Okay, cool. So basically the algorithm is for the X place, we have 3 tokens: 1, 5, and 10. Okay. Now, why am I a little sort of precursor to why am I doing why this is a bit of a precursor. So the reason why I'm doing this is I foresee that we're gonna have some logic that's gonna apply to the 100th place. There is some logic that will apply to the 10th place, the same logic with different symbols. And then finally we apply the same logic once again to the 1st place. Same logic, different symbol. So because I'm already thinking ahead to how I want to structure my code, I can see that parallel, because we're going to break it down by digit, we're going to have some logic for the thousands place. And this logic is a little bit unique because the most we can get is 3000. The most we can get 3000. So the logic for the 1000 place is just M, or MMM. Then we have some logic for the hundreds place, some logic for the tens place, and some logic for the ones place. Now the thing that I'm trying to exploit here is that there is some symmetry in these 3 things, right? Essentially, these 3 things are the same. The only difference is what tokens, what symbols we use. We have 3 different symbols. So for instance, in the ones place, we will have I, V, and X. In the hundreds place, we get C, D, and M. Okay, so that tells me that I would have to say digit to Roman. Actually, you know what? Let me do it the old-fashioned way first. Let me do it without exploiting that symmetry. And then we will start to exploit the symmetry and see why we want to do it, and contrast this with the design choices we made the last time. So the last time, we are faced with very similar idea of symmetry between the digits, right? If you remember what happened the last time, let me see if I can grab that real quick. Yeah, I'm just going off on a bit of a tangent right now because so right now what I'm talking about is we're not actually solving the problem. I'm talking a little bit about an appreciation for what kind of code looks best and is most easy to read. Now, the last time we did something like this, if you remember the problem from a few days ago, we definitely have symmetry. Remember this? There's I, there's X, these pieces of code look mostly the same, okay? And then I introduced the 2 principles, which is 1, dry, don't repeat yourself. And then there's wet, which is write everything twice. Right? Dry and wet. So we talked about why I made the choice to duplicate these pieces of code rather than factor them out into a common function. The reason I did that was 1 is repeated 3 times, which is not a horrible number of times. And 2, the piece of the code are not that difficult to understand. They're not horribly complex. Let's see how horribly complex this logic is, and if it is worth refactoring out into a separate function. In all honesty, though, I'm pretty sure I am going to factor the logic out just to show you guys how it's done. Okay, so the first thing we need to do, but we're getting ahead of ourselves. Let's start with writing the logic for the thousands place. We have, let me see, answer equals to, let's just call it Roman. I don't like generic variable names like answer because it doesn't say what it is. We know that it contains the value of the answer. But what is this answer? What question is this answering? We don't know. Well, we do know, but it takes a bit of time to parse. So Roman equals to nothing. Okay. So first thing we do is extract digits for thousands place. Let's just call it extract digit equals to num / 1000. Easy peasy. I wonder if we're going to do a match here. Match digits. And then we'll do case. I could do that, or I can group the cases. You know what? I don't even have to do that. Plus equals, because the logic here is we just have as many m's as there are digits. So we'll just do digit times m. So if there are no thousands, it's gonna be 0. Okay, this is fairly straightforward. Okay, we're gonna keep our code clean. Notice how we added line breaks. We added a little. Judicious amounts of comments. This is always helpful because once again, remember that you write once and you read many times. Very often, somebody else will be reading your code. Okay, so extract digit equals to num 100. So that gives you, let me see. So that gives you something like 19, which is not what we want. We want to quotient 10. So we take num divided by 100 and we take the last digit of that. So num divided by 100 will give you 19. Remember, / means take the quotient and drop the remainder, and then now we take the last digit by doing remainder 10. And now what do we do with the digit? Maybe we can do match, right? Let's do match first. Let's see where we end up. Match digit case. Can I do this? Can I? Okay, this is what I'm thinking of. Digit 0 3. Can I do something like this? Python case switch. I don't know. Okay. Hmm. I'm not sure. A switch pattern. Structural pattern matching. That's not useful at all. I'm sorry for my buzzing phone. K switch. Switch. You know what? Let's do it the old fashioned way. Let's do an if statement. So there are a few cases here. There is 0 if digit equals 0, L if digit between 1 and 2 and 3, L if digit equals to 4, or digit equals to 5. There are quite a few cases here. And then there is the 6 to 8. And then there's 9. There's no 10. Because a digit cannot be 10. Okay. Cool. Let's write it out fully here. We're going to be a little bit verbose. And it's alright because we're going to think about how to make this a little bit pretty. Yeah, once we're done. So Roman plus equals, you know what? String equals to nothing. Let's just call it R, Roman digit equals nothing. Equals to digit times. So this is the hundreds place, right? If the hundreds in the hundreds place, we have we have 1, 2, or 3 in the hundreds place. Then we simply have 1C, 2C, or 3Cs. So C, CC, and CCC. So this is very similar. To this, except that we add a D in front. So DC is 600, DCC is 700, and this is not digit times C, but digit minus 5 times C. Yep. And for 4 equals to CD, and then 5 is just D. And then 9 is CM. Yep. I probably should have done the ones place first, because that's a little bit easier. So, okay, cool. So now we have this, and then of course we do Roman plus equals Roman digit. Now, Now we've reached a decision point. So there are two ways we can do this. One is we copy and paste this and put it here and here and we modify it slightly. We could do that. My argument is that this is long enough that I don't want to. You look at this. This is not that long. Or at least to me, mentally, it's not that complex. And the other thing is factoring these specific pieces out can be tricky. Like there's a 90 here, there's 40 here. You need to have a hierarchy of LCs, blah blah blah. So that's a little bit tricky. So this one lends itself to refactoring much more naturally, and so that's how we're gonna exploit it. Well, I'm gonna do one other thing that may not be super obvious, which is I'm gonna extract this one line of code out to a separate function. Now, it may not seem obvious why I'm doing this, right? In terms of word conciseness, I'm not saving anything. I might even be increasing the number of words I have to write. But the difference, I will claim, is that this makes it easier to understand what's going on. So, for instance, if I do this, I compare this line over here, line 15 and line 16. You can see that line 15 clearly says digit equals extract digit, num 100. So you might say, hey, we're extracting the 100th place digit from num. Right? So that becomes fairly obvious. Whereas if you see a formula like this, then your brain have to tick a little bit and think, what exactly am I doing this? What exactly am I doing here? So I can take away this comment. I as a general rule, I don't like comments who contain a lot of words that are also replicated in the code. So it says here extract digit. It already says here extract digit. So I don't think this comment is adding all that much value. I'm going to take it away. So digit equals extract digit. Okay, and then I have digit equals this blah blah blah. Now I'm going to take this out and put it in a separate function. Digit to Roman. And I'm going to say, oh, I need to follow I need to follow good principles here. So digit to Roman. Oh, it's int. Digit to Roman returns a string, and it takes in a digit. So this is very interesting. I want to talk about this a little bit. Notice how the type of digit is int. Well, the type of digit, strictly speaking, in its narrowest, most constrained form, should not be int. It should not be an integer. It specifically should not be a 16 or 64-bit integer, which can be huge. And in Python, of course, int is effectively of unlimited size. So in theory, conceptually, you might say that digit is not of type int, is of type 0 to 9, right? But in Python, we don't have an easy way to express the idea of 0 to 9. Now, in some of the languages, you might imagine there's a type called digit. For instance, there's a pair type. There's a very famous conundrum, very very similar conundrum, where people use an array of size 2 to represent a pair, so like a pair of coordinates. In theory, that array of size 2 is not constrained, so you could pass in an array of size 100. The program that am I talking about strongly typed languages here will not make that check. Okay, but so what people want to do, what you want to do in general, is to make your type as restrictive as possible. If your digit here, the values that this digit variable can take is only from 0 to 9, then ideally, you don't want to give it a type that is integer. Not only is it a waste of space, it allows potential problems to go uncaught. Somebody might pass the number 1000 to digit to Roman, and this function will fail, and we will not know that statically, and we will not even know that at runtime when this function is called. It will fail silently, it will give some garbage result back, and the bug will only manifest itself much later on. Okay? So in other languages, there are ways of constraining this integer to only 0 to 9. There is, I don't know, annotations or like some kind of type theory that allows you to do that. But in Python, that is not supported as of this moment. I wish it were, but it's not. Okay. That's just a bit of my rant. So I'm going to take this out, paste this right here, return Roman digit. Okay, so in addition to digit, I need 3 other things. I need the 10, which is a char, 5, which is a string, and 1, which is a string. I don't remember if Python has chars. No, Python does not have char. It turns out. Does not have a character type. It's simply a string of length 1. So once again, you see that those pros and cons, right? So by allowing my type, by specifying my type as string, I'm allowing someone to call this function, potentially call this function, with a string of length anything. When in fact, what I really want to do, what this function really expects, is that 1, 5, and 10 must each be called with a string of length 1 and exactly 1. In fact, people can call this function, somebody might call this function with 10 equals to the empty string. It will still work. It will give you the wrong answer, and somewhere down the line, some bad behavior will manifest itself, and you'll be confused, and you'll be wondering, why is this like this? Okay, so that's just my little bit of rant. So just to follow good software engineering practices, I would comment this function. Okay. Well, if I'm writing this code for real, I would definitely write a little bit more information here, because somebody who reads this. So the idea behind commenting is that somebody should be able to read just this and the comment and figure out what's going on in the body. Sometimes people can read just this and figure out what's going on in the body. For instance, this function is fairly self-explanatory. This one is not. Well, it is kind of is, but you know, it's good to add a little bit more information there, especially constraints like these. So this way, years down the road, when somebody's digging up your code and when they're debugging, and they put a breakpoint right here, and they will realize that, hey, this function is being called with an illegal value for 1 or 5 or 10. Okay, so enough of this. I'm meandering. I just noticed something, which is I don't need a special case for digit. I can just do with digit. is smaller than 3 because 0 times c is 0. In fact, I can do this also. Let's fix it later. Okay, cool. So now this c is actually 1. 1 plus 5. This is 5. 5 plus 1. And then this is 1 plus 10. So 1, 5, and 10 are all symbols. This plus is interesting. 1 plus 5 doesn't give you 6, it gives you 1, 5. Because these are both symbols and strings, and we're doing concatenation here. Okay, cool. So we will logic for the hundredths place. I don't need digit equals extract digit. Instead, what I do is Roman plus equals digit. Oh, I do need digit equals extract digit. To Roman. I can actually put this inside here directly. So 10, 5, and 1. I don't know why I got it backwards, but either way. So 10 is M, 5 is D, and 1 is C. I don't need all of this. In fact, I can just copy this. See, you can make your code a lot easier, a lot shorter. So that there is a common misconception where people conflate terseness or conciseness with readability. This is not always the case. This is sometimes the case. A shorter piece of code is often easier to read, but it's not always easier to read. So you have to be careful about this. Okay, and then logic for the ones place. X, V, and I. Okay, cool beans. Alright, so this should work. Let's see what happens when I run it. Extract digits is not. Oh, do I have to do this? Yeah, I probably should figure out how to do this the right way. So self.extract digit, self.extract digit. And then I do self dot all these things. Num is not defined. Wait, what? Okay, let's fix all these first. Num line 3. Oh, it's not it's n. Wrong answer. 3. I get nothing. This is embarrassing. Okay. So I did notice something I didn't know before about LeetCode, which is you can actually put a breakpoint right here. Let's see what happens when I run with the breakpoint. Oh, I'm sorry. This should be fairly obvious. Okay, let's run it again. Okay, so when you get an error like this, the best way, the best strategy of dealing with errors is to break it down. And let's see what's happening at each individual place and sort of diagnose where the problem is. So we'll go to our trusty Python tutor. I'm pretty sure LeetCode allows you to have a better IDE support. Yeah, I might investigate that next time. In the meantime, let's just do this. S dot int to Roman. 3, right? Okay. So we're running. All right, let's see what happens when we get to here. All right, so far Roman is nothing, which makes sense. Let's go in, step in. It goes to extract digits. So return value 0. Oh, I see. Yeah. So it should be place. Let's make this also place. Oh, oops. Okay, now it works. Now it works. Let's submit it and see what happens. All right, perfect. Beats 89.24% of users with Python 3? No way. How did that even happen? I'm using this old ass computer. This is a very old computer. Well, it's not. This is not a great computer. So I'm surprised that I actually beat people on this. Also feeling a little bit proud. Ain't gonna lie. Let's see if this beats even more people. 98.89%? That's insane. Why is this so quick? I'm curious, what do other people do? Easier Fang method ever. I don't know about this. I don't like this solution. Well, okay. Let's look at this guy's solution. I like and I also dislike this solution for a few reasons. So one, what I like about it is that it's concise, and the thing about the thing I said about being willing to repeat things a few more times. This guy basically took it to the max. This guy basically took that principle and just ran with it. It just added more stuff. And I guess, yeah, maybe this is the right way to do it. Maybe this is just a more concise way of doing it. Yeah, you know what? Maybe he's right. Maybe I'm wrong. Yeah. Now looking at this piece of code, I'm more and more swayed to this solution. It's simpler. And because this is just 10, this is not like 1,000. And Roman numerals don't change much anyway. So imagine if Roman numerals were gonna change a lot, or we're gonna add many more digits, right? Then this becomes a very valuable function. But because there are only 3 digits here, this function is not particularly valuable. I think this solution is better than mine. Cool. So that's it for today. Before we end, let's go back to our top 150 problems. How do I go back to that? Study plan. Okay. And pick one that we'll do next time. All right. Let me see. The mediums are not that difficult, so maybe I'll do a medium next time. Zigzag conversion. It's written in zigzag pattern on you might want to display. What is this? PayPal. PayPal is hiring. ISHR. Okay. All right. Wait, what is the zigzag pattern? Oh, okay. So I see the zigzag pattern. It goes down, and then it goes up, and then comes back down, and it comes back up. Oh, interesting. Okay, so let's do this problem for next time. So our homework, well, homework. Our problem for next time will be zigzag conversion. Yeah, next. Save. How do I access new lists? Duplicate. Can I access my own lists? Nope, I don't see where to access the new list. My list, there we go. So we have next. Okay, so we have zigzag conversion next. Okay, perfect. So I guess we are done for today. Thank you once again to everybody for logging in. Feel free to follow me. I stream twice a week these days. It's going to be 10 a.m. on Sundays and Wednesdays. I'm going to try and figure out a more steady schedule. And you can catch all of my old videos on YouTube Live. Signing out. Bye.